Hey everyone, and welcome to This Explainer. Today, we're taking a deep, really fascinating look at the modern AI engineering interview gauntlet. Whether you're gearing up for your next big career leap, or you're just kind of curious about the incredibly rigorous standards shaping today's AI engineers, we're going to break down the exact trials and triumphs that make up an ML model's hero's journey. We'll be going from fundamental theory right up to deploying massive Gen AI systems.
Okay, let's dive right into our roadmap for today. We're going to start off with nailing ML fundamentals, then move into debugging production nightmares, escalate to taming the scale monster, and finally, we'll face the Gen AI final boss.
Let's kick things off with Act 1, nailing ML fundamentals and building that foundation.
You know, one of the absolute core concepts you're going to see tested in almost every single interview is the bias-variance tradeoff. It's really the ultimate balancing act. You're trying to capture complex patterns, which means low bias, without being overly sensitive to weird fluctuations in your training data, so low variance. Minimizing both of these is exactly how you avoid the dreaded underfitting, where you just miss the pattern entirely, and overfitting, where the model essentially just memorizes the training data.
Right, so once you've got the theory locked in, you have to actually train the thing. And that brings us to hyperparameter optimization. Let's be honest, we have all felt the sheer pain of burning a 100-hour compute budget on a terrible learning rate, right? To avoid that, elite engineers use a really strict budget. Step 1 is a quick exploration. You use about 10% of your budget with a random search just to eliminate the obviously bad regions. Step 2 is focused refinement. You spend 30% of the budget using techniques like successive halving or Bayesian optimization to really zero in on the best configurations. And finally, Step 3 is final validation, where you use your remaining 60% budget to train your top configs to convergence on a holdout set.
But there is a golden rule here to keep in mind. The best hyperparameter search is the one you don't run. Seriously, before touching that compute budget, the smartest first move you can make is transferring known defaults or looking at prior research. If a specific learning rate works for a very similar architecture, just start there. Being strategically lazy is actually a highly valued trait.
Moving right along to Act 2, debugging production nightmares. Time for a reality check.
All right, picture this. You're in the hot seat, and the interviewer drops this classic prompt. Your model performs perfectly on the validation set, but it totally tanks in production. Why? It's the dreaded train surf skew. But the catch here is that the interviewer isn't looking for a lucky guess. They want to see a systematic troubleshooting framework.
A systematic diagnosis means working down the usual suspects. First up, data distribution shift. Are users just behaving differently now? If not, you check feature computation. Are your time-based features calculated differently in real-time serving compared to batch training? Then look for pre-processing inconsistencies, something like a mismatched tokenizer version. And finally, the silent killer, label leakage. Diagnosing this is actual detective work, ranging from tracking user shifts to hunting down really subtle infrastructure bugs.
And while you're doing that detective work, it's surprisingly easy to fall into the trap of mixing up concept drift and data drift, especially under interview pressure. Concept drift is when the target itself changes, like spammers inventing entirely new tactics. Data drift, on the other hand, is just the input values changing, like your app suddenly trending in a new country. Knowing exactly which one you're dealing with completely dictates how you fix the system.
Okay, let's level up. Act 3, taming the scale monster. What happens when those 80 gigabyte GPUs just aren't enough?
When you hit that memory wall, you need distributed training. Think of it like a massive manufacturing plant. Data parallelism is like having multiple identical assembly lines processing different batches of raw materials. Model parallelism is when a single machine, like a huge attention layer, is simply too massive for one room, so you literally split the machine itself. And pipeline parallelism splits the model vertically, like passing a product from room A to room B. It's absolutely perfect for incredibly deep models.
But what if you need to shrink the model for blazing fast inference? Well, that requires the compression rule of 3. First, quantization, dropping numerical precision from a 32-bit float down to an 8-bit integer. Second, pruning, taking shears to the neural connections that don't heavily impact the final output. And third, knowledge distillation, where a massive teacher model trains a tiny, super-fast student model to mimic its outputs. It's a really elegant balancing act between size reduction and inference speed.
And that brings us to our final act. Act 4, the Gen AI final boss. Welcome to the modern era.
So, here is the ultimate question they're going to throw at you nowadays. How do you handle tasks requiring way more context than the model can take in at once? Despite massive advances in modern hardware and slick memory management techniques like page detention, the context window is still a fundamental limitation. It's an incredible hurdle because you just can't feed a 10,000-page corporate archive into a single prompt and expect perfect performance.
Which naturally leads right into the classic RAG versus fine-tuning debate. It is all about knowing which tool solves the problem. You lean on Retrieval-Augmented Generation, or RAG, when you need the model grounded with dynamic, private, or super up-to-date facts. Conversely, you turn to fine-tuning when you need to bake specific behaviors, formatting, or a proprietary tone permanently into the model's weights. Think of it this way. RAG gives you facts, while fine-tuning gives you style.
Now, combining these tools gives you a multi-layered defense against the absolute ultimate nightmare, hallucinations. You are essentially building a wall, brick by brick. You start with RAG for that factual grounding. Then, you add chain-of-thought prompting to force the model into step-by-step reasoning. Next, layer in self-consistency by generating multiple answers and picking the best one. And finally, you cap the whole thing with post-processing guardrails to fact-check the output before the user ever even sees it.
Which really brings us to a pretty provocative question to wrap things up. If these models are now writing their own code, what exactly is the ML engineer's job tomorrow? As we've seen today, the role is shifting. It's becoming about diagnosing systemic drift, architecting massive infrastructure, and designing bulletproof guardrails. The tools are absolutely changing, but the need for deeply structured architectural thinking is only growing. I hope this explainer leaves you feeling empowered to tackle these exact challenges. Keep learning, keep building, and we'll see you next time.